I'll be talking to you about Aditya L1 mission. My name is Durgesh Tripathi, and I'll be talking to you about this mission on behalf of the Aditya L1 team. And there is always a big team who works towards the success of such missions. In this slide, essentially, you see data. They are real data taken from earlier spacecrafts from NASA and Japanese space missions. At the bottom, in the middle, you see that's from the ground-based telescope. So Aditya L1 is going to provide you all kind of data what you see here, and the spacecraft, which is Aditya L1, is seen at the bottom left. So before I move on, the way I would plan it, like I'll tell you what are the pressing science questions in solar physics, and what actually you need to address those problems, and then convince you that a mission like Aditya L1 will essentially help you address those science questions. So you in earlier lectures you must have learned about this, that the structure of the solar atmosphere has essentially three parts. Is the photosphere, the chromosphere, and the transition region and corona. And this plot is essentially showing you this, that when you go higher into the atmosphere, the surface layer is the photosphere. That's what you see when you look at the sun from ground, because that's the visible light emission which comes all the way till the ground. And then when you go higher into the atmosphere, the temperature starts increasing in the chromosphere, and this thin layer is called the transition region, which is only about 100 kilometers thick, and the temperature reaches till about million degree, where at the top of the chromosphere the temperature is only about 30,000 degrees, and it reaches a million degree at the top of the transition region and goes to even beyond a million in the corona. This is the outer part of the solar atmosphere. On the other hand, the density, when you go out, that just falls and sharply falls in the transition region. When the temperature sharply increases, the density sharply decreases, and it goes all the way lower into the corona. Just to compare with some of these numbers, the highest density in this plot, so that's the density curve that goes to more than 10 to the power minus 8. That's the kilogram per meter cube, and that highest density is still about what the density you will get in the Earth atmosphere if you go 90 kilometer up. So it's pretty tiny when you compare to density what we feel here. Similarly, the temperature is much larger, and is really much larger than what is the melting temperature of silver is, for example, or the kind of temperature you feel when you do welding. So these are just the numbers to put in perspective, but the real issue here is that when you go away from the sun, the temperature increases, which is counterintuitive, because we know, as you have learned in earlier lectures, that there is a nuclear burning going on in the core of the sun, and that's where the temperature is around 15 million degrees. When you go out, it decreases till the photosphere, but then it starts increasing. So that is one of the pressing questions solar physicists have to look at. And because of this, if you take different parts into the solar atmosphere, and since the temperature is increasing, they are radiating at different frequencies or at different wavelengths. So you can design telescopes to look at different layers of the atmosphere. So what is done here is a collage of solar images taken from different telescopes. So this here is taken in visible light, that's imaging the photosphere of the sun, and then the way you are going higher into the temperature, you are mapping different heights into the solar atmosphere. What you see is that depending on the height in the atmosphere you are looking at, or depending on the temperature of the sun you are looking at, the sun looks very, very different. For example, in the visible light, you have this orange disk, which you know the sun looks like orangish. When you go higher up, you have sun looking very structured. So, you have bright structure in here, and then there are other not so bright structures, but you go even higher, then you have really bright and really dark structures. This image here is essentially the magnetic field map of the sun. So, what you do, you take each point on the sun and you do Zeeman splitting or Zeeman spectroscopy, and you measure magnetic field at each point on the sun. What you find that the sun's surface is full of magnetic field. So, what is shown in white here is the positive polarity, whatever is shown in the dark is the negative polarity. And what you also find that the locations where you have a stronger magnetic field, that those are the regions where you have much brighter structures forming into the upper layers of the atmosphere. So, that gives you an idea that it has the higher temperature into the upper layers of the atmosphere must have something to do with the stronger magnetic field, which is again generated deep down inside the surface of the sun or within the sun, that you must have learned in the solar dynamo in earlier lectures. Now, the other way you look at the sun is during eclipses. That does not happen all the time, once in a year, and that too in different part of the world. But what you see is like when the moon comes and blocks, you see outer structures in the solar corona, and it's called corona because it looks like a crown around the sun, and you see that it's very highly structured. Now, we know that these structures are nothing but representation of the solar magnetic field and the electrons contained in those magnetic field. Because the temperature is so high, the plasma is fully ionized and the plasma is trapped within those magnetic field. So, when the photospheric photons are coming from the background, they are getting Thomson scattered by the free electrons, and therefore, whatever bright structures you are looking at into these eclipse images, they are representing the magnetic field as well as the electron density distribution into the corona. Now, unfortunately, we do not have a direct way to measure magnetic field into the corona. So, you have to look at some indirect ways of understanding what the magnetic field topology is like. One of the ways is that since we have a good measurement of the magnetic field on the photosphere of the sun, we can use that as a boundary condition and try to map the magnetic field in the corona. And on the larger scale, so this is one of those simulations where you take the magnetic field on the surface and extrapolate using that as a boundary condition, extrapolate the magnetic field in the corona and match the structures whatever you see in the eclipses. And you see that on a larger scale or rather global scale, we do a good job. For example, here on this area you see these open field like structures which you reproduce very well in your simulations. Similarly, these streamers or closed field structures, that also is very well produced, but it has limitations. And on the smaller scales where you have much more complex magnetic field, it tends to not do such a good job, and therefore, we would really like to have a direct measurement of the magnetic field. The reason that we do not have direct measurement of the magnetic field in the corona, because if you want to do Zeeman splitting, you need to have some certain strength of the magnetic field which will split the magnetic field lines or the spectral lines. At the same time, the temperature has not to be very high, otherwise the thermal width of the line will itself be very large. So, in the corona, when you are looking at a 1,000,000 degree plasma, the spectral lines are already so broad and the magnetic field is so weak that even though if there is a Zeeman splitting, you would not be able to detect, and that is the problem. So, that is one question which everybody in the world is looking for, to how actually to measure the magnetic field in the corona to a precision where we can say something about the dynamics of the magnetic field, and that will also help us understand how the magnetic energy is essentially dissipated into the corona to heat it to a 1,000,000 degree. Now, since we have different layers we can map, and we have the sun is so close by that we have a lot of photons. We can also take images on time scales that we can look at evolution of different features, the way it grows in the atmosphere. So, for example, here in the top left, we have an animation which is created using real data taken from SST, Swedish Solar Telescope, where you see a sunspot, the granulation and the filamentary structures evolving within the sunspot. So, that gives an idea about how different features form, how different features gets heated, how different features get faded away, and so on and so forth. Similarly, in the top right, you see it's taken from Hinode telescope, Hinode Solar Optical Telescope, and this is only a part of the sun where you see a plasma structure is just hanging within the atmosphere. Now, in usual sense, this should just fall back to the surface because of the gravity, but then there is some force which is holding it up, and that has to be magnetic field because there is no other force or acting there. In addition, you see other structures like spicules, hair-like structures just wobbling around. In the bottom left, you see 3 different temperature component of a flare. So, 3 different telescopes looked at that particular flare event, and those data were taken simultaneously, put together in 3 different colors, and that shows that how multi-thermal the structure could be when you are looking at these flares. And then in the bottom right, you see other tiny small scale events taking place, which are called jets and bright points at time scale of every minute. So, that essentially tells you that the solar atmosphere is such a dynamic regime, such a dynamic area to look at, that you want to understand how these small scale events are coupled with the large scale events, if at all, and how actually what produces these flares, what defines the multi-thermal structures, and so on and so forth. Even larger scale structures, you have these big prominence eruptions. So, these are the materials, the cooler plasma, which are seen in absorption, hanging in an environment of a 1,000,000 degree plasma. So, you have a 1,000,000 degree gas, within that you have 20,000 degree gas, which is hanging with the support of the magnetic field, and the lifetime of those structures could be about a month. Suddenly, it decides to erupt and gives you the mass ejections, which are engulfing the interplanetary medium, which are called coronal mass ejections. So, this is one of the examples taken from Solar and Heliospheric Observatory. So, what is done here is artificial eclipsing. So, you see at the center the white ring is the sun, and then you block the sun and some other some areas around the sun, so that you block the really bright light to look at the fainter structures in the outer atmosphere. And you see that there are a lot of structure in the corona, even going from 4 solar radii to 30 solar radius, which are always there. But then on top of that, you have these sudden ejections of the mass, which is engulfing the interplanetary medium with plasma and energetic particles, and they are the one which are creating space weather effects, such as if they are geomagnetic, then they could create aurorae even at lower latitudes. It can create satellite communication issues, electric power blackouts, and so on and so forth. Now, how actually we define space weather. So, the space weather is defined in a way that the environmental conditions in the Earth's atmosphere, which is magnetosphere, ionosphere, thermosphere, due to the sun and solar wind, that can influence the functioning and reliability of a spaceborne and ground-based system and endanger property or human health. Right. So, there are 2 kind of space weather effects we have. One is the short term, where you have these coronal mass ejections or the flares, the sudden ejections of plasma and energetic particles, which are engulfed into the interplanetary medium, and eventually if they are directed towards the Earth, they come and hit the Earth's atmosphere. And the other is the long term, because the sun's radiation is always there, which is emitting, as you could see, all the way from infrared going all the way till X-ray. And we know that the X-ray and ultraviolet gets absorbed in the atmosphere of the Earth. So, that is going to govern in some way the dynamics of the Earth atmosphere, and that gives somewhat a climate pattern observation in terms of ozone and oxygen chemistry, and even the inflating and deflating of the Earth atmosphere. So, the way the coronal mass ejections affect, so here is another observation of taken from SOHO, which is LASCO C3, and you see all these mass ejections are coming. So, only those are relevant for space weather are the one which are coming towards the Earth, and also if they have a southward component in the magnetic field, because that is the only time when the Earth's magnetic field can get directly connected to the sun's magnetic field, and all these energetic particles are put into the Earth's atmosphere through the magnetic field coupling. Here is a simulation done for one real event, where you see that the sun is on the left side, that is the day side, and then the night side. So, you see the magnetotail of the Earth's atmosphere is just elongated because of the solar wind, and on the left side, because of the radiation pressure from the sun, the magnetic field is pushed towards the Earth. Now, at the bottom left of that figure, what you see that shows the direction of the magnetic field in the ejecta which is coming from the sun. And on the bottom right, you see as if you are looking at the pole of the Earth from the top. If you look at these carefully, what you find is that as and when the magnetic field in the ejecta goes towards the southward, then you see a lot of ring current and aurorae formed on the polar cap regions on the north pole of the Earth. So, that essentially tells you that when you have the magnetic field pointing towards the south, the magnetic field gets connected to the Earth's atmosphere, drags around on the other side or towards the night side, that reconnects again, puts the charged particle towards the pole, ionizes nitrogen, and you start seeing these aurorae in the atmosphere. Now, if these charged particles can enter to electric pipelines, because they are conductors, they can go and burn your transformers. So, that can give you further impact on electric power blackouts. Now, how do we know that which coronal mass ejection is going to be geoeffective? And what people have done so far is to look at the magnetic field on the surface, because that is where we can measure, and from there try to predict or look at what kind of topology the ejecta is going to carry, and if that is going to be geoeffective. What is found that the chances are always 50-50 or 40-60 if you like, and the reason is that the coronal mass ejections, of course, they have to begin with they have a magnetic field configuration, but while they eject, they go through a lot of dynamics, and a lot of changes do happen into the topology of the magnetic field. So, for example, here is an observation of this prominence which is being ejected at a coronal mass ejection. Now, while it rises up, it goes through kinking, and the kinking lets this to rotate. So, even if at this location the topology is such that this ejecta is going to be geoeffective or not, by all these rotations you never know if you can say that this is going to be geoeffective unless you measure the magnetic field by the time when the ejecta has happened, and also in the interplanetary medium before it actually goes and hits the magnetic field of the Earth. Here is your simulation, and you can see that all these field lines are drawn, and the way the ejecta is rotating, you really have very little chance to predict anything just by looking on the surface of the sun. Therefore, you need to have measurements at the surface, in the corona, also at the location somewhere in between the sun and Earth, so that you can still predict that this ejecta is going to be geoeffective. In addition, what you have is a problem of good handling of the kinematics. Even though if you can predict that this ejecta is going to be geoeffective, you really also have to predict that how long it's going to take to travel to you and hit the atmosphere. So, you really need to understand the kinematics of these structures very well. What we found so far is that the coronal mass ejections, 90% of them show most of its acceleration within the early phase of its rise. Later on, it just gets dragged away by the solar wind. Unfortunately, we really do not have observations in the range which is within 1 to 2 solar radius, which can help us understand the complete acceleration mechanism. We have eclipses and we have ground based telescopes, but then ground based telescopes, the cadence is not that good, and secondly, half of the time it is night. The eclipse happens once in a year. We had LASCO C1, which was imaging that part to some extent, but it did not work for a very long time, only 2 years. So, we do not have good enough statistics. The rest all the coronagraphs are looking beyond 2.5 solar radius. So, we really do not have good handle on the kinematics during the proper acceleration phase. What we also know that is also the region where a lot of things do happen in terms of dynamics. For example, here is an observation where you see that there are 3 phases. So, one is the core or the prominence, which you see in the UV images, and then the other part is the leading edge, which is on the top of the prominence or the flux rope, if you like. What you see in the beginning, it rises pretty steeply, but then it goes to deceleration phase in beyond 2.5 solar radius and continues. That is the core, but the leading edge, which is above that, it seemed to be disentangled completely and it follows a completely different path. So, this guy goes with a speed of around 900 kilometers per second, whereas the core of the structure only propagates with 250 kilometers per second. So, now which one you should take, the leading edge to be geoeffective or the core to be geoeffective? And also, as you can see in these movies here, they are the structures where a lot of motions and activities are happening. You have reconnections which are letting some plasma go down towards the surface, only a part of the plasma which goes up as a coronal mass ejection, most of the plasma just falls down. So, and that happens exactly within the range which is 1.5 to 2.5 solar radius, and that is where we do not really have good handle from observational side. Here is Ander, which talks about the kinematics, and what we know is that when the prominences start to rise, they show a very slow rise phase and then suddenly gets accelerated. The idea is that this probably would be caused by small scale reconnection processes, and then once the system becomes unstable to ideal MSD instability, it just jumps into another state of equilibrium, and if there is nothing to support it, then it just keep rising and goes as coronal mass ejection. In this particular case, we know that this is reconnection because we see that hard X-ray source emitting at the same location where one of the threads of this prominence was rooted, and then later on after the hard X-ray, plasma just cools down and then you start seeing it in soft X-ray, and as you can see, this prominence just goes on and erupts as a coronal mass ejection. The other thing what we see is when you look at the spectrum for this hard X-ray burst, we see that there is a component of non-thermal emission, and that again justifies that this non-thermal thing is coming because magnetic reconnection is taking place. Now, these are the short term effects which are flares and coronal mass ejections, but when it comes to long term, we know that the sun is emitting all the way from infrared, which is here, all the way till X-ray. Now, the X-ray and UV irradiance is absorbed by the Earth atmosphere, and the changes in X-ray and UV irradiance affects the thermosphere, ionosphere, and near Earth space. This line is Lyman alpha, which you can see is really bright, and that changes very strongly with the solar cycle. What we know that when these radiation they come towards the Earth, This is the height in the Earth atmosphere. This is the temperature plot. This is during solar minimum. This is during solar maximum. And what we find is that from solar minimum to solar maximum, the temperature in the Earth atmosphere changes by around 400 Kelvin. Now, if you have a gas and you heat it up, the gas is going to expand. So, the Earth atmosphere is not static and is highly dynamic, and one of the reasons of being highly dynamic is the solar activity, because the high energy radiation is absorbed and then the gas essentially shows expansion or shrinkage the way the solar activity goes. And that leads to another space weather effect, because if you put a satellite in the space and the gas is shrinking or expanding, that provides a drag force, and that will actually destabilize the spacecraft. So, you have to, if you want to keep the spacecraft at a level in an orbit fixed, then you have to keep boosting it to that particular height by giving extra energy. And this wasn't known earlier, because Skylab, the lifetime was about 5 years, but it only worked for 2 years, because at that time, that was only in 70s, we did not know the effect of the sun's radiation. The other effects are really long term. So, we know that the total solar irradiance varies slowly on decadal and longer time scales, and over a solar cycle it changes by 0.1%. Most of the reconstructions show that the total solar irradiance point to only a small increase of about 0.05 to 0.1% between Maunder minimum and present. So, Maunder minimum was, you must have learned, is the activity when there was no sunspots on the surface of the sun, and now we do see number of sunspots, but the change in the total energy output is only up to 0.1%. And that is the plot which shows from cycle to cycle how much energy changing, and look at this scale, it is very tiny. This shows that only 0.1% change has been observed in the total energy. But what we also know that the solar irradiance, that is the total solar energy, whereas if you look at the total solar irradiance and its variation with the wavelength, it shows a very strong dependence on the wavelength. On the whole, up to 60% of the total irradiance variations are produced at the wavelength below 4000 angstrom. So, here is a plot. It shows the relative contribution to the total solar irradiance as a function of lambda. The bin sizes here are done in there are different bin sizes on x axis, that is why you see this dip in the solar irradiance. So, the red shows that the contribution here, and what you find that this below 400 nanometers or 4000 angstrom, only 8% is the contribution. So, the total energy contribution by the radiation below 400 nanometer is only 8%, but this blue here shows that how much does it change over a solar cycle, and we find that the radiation or the energy content below 400 nanometer radiation changes by about 60% from solar maximum to solar minimum. And remember that is the energy which is absorbed by the atmosphere, and that is why it creates so much of dynamics into the atmosphere of the Earth. So, these are divided in UV A, B and C, and what you can see is that A, B and some part of C all the way comes to the stratosphere, and that is where your ozone layer is, and that changes the ionization and dissociation of oxygen and formation and ionization of ozone. So, that plays a very important role in the stratosphere. And what we know is that this radiation, which is below 400, comes from the chromosphere, transition region and the corona, and this particular region which is 200 to 400 nanometers, which is really affecting the stratosphere, that comes from photosphere and the chromosphere, and that is very important region to understand if we really want to say anything concrete about the dynamics of the ozone layer or the stratosphere. And this plot essentially shows that how much we understand about this particular range in the wavelength. What is shown on y axis is the difference in the spectral irradiance below 242 nanometer on x axis, on the left x axis, and on the right y axis you see the difference beyond 242 is going all the way till 700 nanometers. So, these are two instruments, Solstice and SIM, shown in two different colors here. And this black curve here is the state of the art modeling, whatever we know so far as a proxy for measuring the irradiances. What we see is from observations and models, we have about factor of 4 to 6 difference. So, that means there is something which is really crucial we are missing, and we are not being able to put that ingredient in the modeling to get that right to the observation. But there is a glitch. The glitch is that all these observations are the proxies which has been put in so far in this particular wavelength range is done by using sun as a star. So, considering sun as a point source, so take the total energy in that particular wavelength. But as we know, the sun has a lot of structure, and any tiny change can give a lot of changes in the variation of the irradiance, and therefore, we need to understand structure wise how these things are changing, and therefore, put that into the modeling. So, the proxies particularly given in these models are not complete. So, here is again going back to that collage. Considering that this part here comes from this region of the solar atmosphere, which is the transition region, the corona, and since the temperature increases really fast and density decreases really fast, a lot of attention has been given into this upper layers of the atmosphere. Whereas, this part here, which is the photosphere and chromosphere, although photosphere has been observed from ground, but not in ultraviolet, because you have to go to space to look into ultraviolet, this region has not been so well studied. So, that is another area where one should need to focus, to not only to try to understand that how the solar atmosphere is coupled, because essentially the magnetic field is coupling all the way different layers of the atmosphere all the way from the photosphere to the corona, but also that how this particular range of radiation is going to affect the earth climate. So, to answer these questions, such as how the sun's radiation is going to affect the earth climate, how can we measure magnetic field into the upper layers of the atmosphere, can we look at the kinematics of these coronal mass ejections, which are going to be geoeffective or not. That means measuring magnetic field not only on the surface, but also in the corona, as well as at somewhere in between sun and earth, so that we still get enough time to give warning that this coronal mass ejection is going to be geoeffective. ISRO has approved this mission, which is called Aditya L1. So, Aditya L1 is going to have 7 instruments on board and is going to be at the first Lagrange point, which is between sun and earth, 1.5 million kilometers from the earth towards the sun, and that is the location which is sort of stable. We have to put the satellite into a halo orbit around L1, and from there you can monitor the sun 24/7, because when your earth moves, the L1 point moves and your spacecraft is at L1. So, it can keep an eye all the time on the sun and look at the activity 24/7. It is going to cover all the way from X-ray till infrared by using all these 7 instruments, and it will not do only remote sensing, but it will also do in situ measurements for magnetic field and the kind of particles the sun is going to produce in different events, as well as in general solar wind, to see if we can not only understand the dynamics of the sun and its environment, but also to predict if the coronal mass ejections are coming and if they are going to be geoeffective. So, the major science goals of Aditya L1 is to diagnose the large as well as the small scale structures in the solar corona, to also provide magnetic field topology and direct measurement of the field in the corona, origin and dynamics of solar flares and coronal mass ejections, and especially resolved solar spectral irradiance, because as I said, the region which is central for sun climate is 200 to 400 nanometers, and so far it has been done sun as a star observation. So, one of the objectives is to now look at the sun in a spatially resolved way in these wavelength and try to measure the changes in the irradiance within this wave band for different structures, and then try to implement these to state of the art modeling for sun climate. Formation and dynamics of the solar prominences, the cool plasma hanging in the ambience of 1,000,000 degree, how actually do they form, what governs them, and why do they suddenly want to erupt as coronal mass ejection. What are the coronal abundances and what are FIP effects, and then also to measure the composition and the interplanetary coronal mass ejections, their composition as well as the magnetic field and their geoeffectiveness. So, the payloads, there are 4 payloads which are going to do remote sensing. The visible emission line coronagraph, which is essentially a coronagraph which blocks the sun's disk, eclipsing and looking at the corona, which is the outer atmosphere. And then the solar ultraviolet imaging telescope, which is looking at the sun's disk now, not doing any eclipsing, but looking at the disk. Then solar low energy X-ray spectrometer, so looking at the soft X-ray, which is going from 1 to 30 keV, and then high energy L1 orbiting spectrometer, which is looking at the high energy. So, the idea is that you cover all the way from 1 to 150 keV. You cannot do it from one detector, you need to have different technologies. So, 1 to 30 and then from, or rather 1 to 50, I will get back to it in this. And there are 3 in situ instruments which are essentially picking those particles which are coming from the sun, measuring their properties. So, one is the Advanced Solar Wind Particle Experiment ASPEX, and the other is the Plasma Analyzer Package for Aditya L1 PAPA. And the last one is the magnetometer, which will sit there, look at the ejecta coming from the sun and provide the topology of the magnetic field in those ejecta, and then tell us if it is going to have a magnetic field which is suitable for it being geomagnetically effective. So, the observations we have so far from eclipses are the emission lines, eclipse corona taken here. So, what you see the prominences on the limb and then a very bright ring around here, but the field of view is very tiny. Then from LASCO C1, which could go all the way from 1.1 solar radii to 3 solar radius, but it did not work for very long time. So, we did not have good statistics. So, we miss everything beyond between 1.1 or from the surface till about 2.5 solar radius, because the only observation we have is from 2.5 to about 6 solar radius by LASCO C2. And then we have the eclipse corona, that is the best thing we ever have, is all the way from the surface of the sun to about 6 to 10 solar radius, depending on how bright and how good the structures are. What we want to do is to cover this range between 1 to 2 solar radius on continuous basis. We only get 3 eclipses once in a year. So, the coronagraph on board Aditya L1 is going to cover this range, which is going from 1 to 3 solar radius in visible channel. And then we also have ultraviolet or a channel no, this is still visible channel, but in the lines which are forbidden lines, and they give idea about the emission corona. So, we will cover that from 1 to 1.5 solar radius, and we will also do spectroscopy using these 4 slits which are there. So, we will use those slits to do spectroscopy and also spectropolarimetry in iron 13 line, which is in infrared. That will be used to then measure the magnetic field in the lower part of the solar corona. So, the questions the emission line, visible emission line coronagraph is going to address is it will provide unique perspective to study the processes occurring in the lower solar atmosphere or lower solar corona, because we are essentially going to do spectroscopy from 1.05 solar radius to 1.5 solar radius, and that is the range where we have a lot of dynamic events happening in the corona. We will also be able to characterize the main magnetic dynamical and thermodynamical processes in the corona. Because of the spectroscopy, we can measure the temperature, density, non-thermal width, and various other parameters to look at such dynamic events. And it will address to the following questions: how is the corona heated? Is it heated because of the transient events, or there are a lot of waves which are dissipating and depositing and dissipating energy in the corona? The crucial issue of the kinematics of the coronal mass ejections, what happens to them early on, how homogeneous or how inhomogeneous the corona is, and its effect on the heating and acceleration processes for the coronal mass ejections as well as the solar wind, and of course, the field configuration, the topology in general way. So, this is the actual data you would get, rather the spec of the data. So, the spectral range, there are 2 visible emission lines we are going to cover for spectroscopy, which is at 5303 and 7892 angstrom, and then the infrared 10747 angstrom line will be used for spectropolarimetry. And then of course, we have the continuum channel, which is going all the way to 3 solar radius, which is at 5800 angstrom. Of course, there are different detector sizes, so the resolution will be better for the visible, the field of view for the infrared will be smaller. The spatial resolution we are getting is 1.2, which is the best so far, and in infrared it will be 4 arcsecond per pixel, bit lower because it has to go infrared, and infrared detectors are rather complicated. The observing time sequences you can get all the way from 1 second to 60 seconds. So, if you really want to do high temporal observations like looking at waves, then you can go for high cadence observations, otherwise you can go for lower cadence observations. So, depending on what actually you want to do, you can propose, and then the spacecraft team or the payload team will look into your proposal and then run that on the experiment to get you the data. Right, the solar ultraviolet imaging telescope, what is it and why is it important? So, this is essentially a combined medium and narrow band filter imager, which is going to image the sun between the wave band of 200 to 400 nanometers. And since we want to look at features, so you do not want to have a lot of stellite, and you want to have really good contrast, so that you can look at bright features versus dark features and monitor their evolution with time. Why is this important? This wavelength band is particularly important because it covers the region from photosphere to the upper chromosphere, and that is the region which has been ignored for a very long time. And since the magnetic field which is generated deep inside the sun goes through all these layers to get into the corona, so this region provides an important ingredient for understanding how the upper layers of the atmosphere is coupled with the magnetic field which you measure on the surface of the sun. It also has additional benefit, or rather more important benefit for sun climate relations, because that's the range of the radiation which is affecting the stratosphere or changing the atmospheric dynamics of the earth. And also the nice thing is that it has not been looked at from space. Of course, Sun as a star people have looked at, and also using Sunrise 1 and Sunrise 2 balloon bound experiment, but not from space 24/7 with such a full disk and such large field of view. So, the science objective of SOOT is to look at the coupling and dynamics of the atmosphere. So, the question it's going to ask or rather address is that what are the processes through which the energy is channelized and transferred from the photosphere to the chromosphere and eventually to the transition region and the corona. The second point is going to address is the sun climate studies. Why and how strongly does the solar irradiance of relevance for the earth atmosphere or earth's climate vary, because it's demonstrated that this particular wave band is really important for the earth climate. The solar flare studies, at what wavelength do flares radiate most of the energy, because so far we have been studying solar flares in hard X-ray, soft X-ray, mostly in X-rays. But what is known is there is a lot of energy, and sometimes about 80 to 90% of the energy is not in X-rays or hard X-rays, but rather in near ultraviolet and white light. So, if you have more flares during the solar maximum, and that we see that the number of flares increases similar as the solar cycle, then that is going to create already differences in the solar irradiance at these wavelengths, and therefore, this is really important question to understand, not only from the flare physics side, but also that how is solar flares are affecting the irradiance in different wave bands. And the prominences, that what are the mechanisms responsible for formation, stability, dynamics, and their eventual eruptions of solar prominences. So, this is what it's going to do. So, it's going to have 11 filters which will be slicing through the atmosphere at different heights depending on what wavelength you look at. So, that's the region it's going to cover, the photosphere and the chromosphere. And from the spectral band, you see that that's the range where the solar spectrum is rising. So, the 214 nanometer, that's the lowest wavelength channel, and the highest wavelength channel is 396, and you can see the solar flux changes by a factor of 15 to 18. And since we only have one telescope, so there is a lot of research and development had to go in to actually how to get the dynamic range of the detector right, so that we get all the photons without undersaturating or oversaturating our detector. And that's the region which is affecting the stratosphere. So, that's the importance. That's how the telescope will look like. So, you have this is an off axis telescope with a thermal filter, and that is something which we designed at IUCAA with a company in Mumbai, and it took us a lot of time because that is one of the most important component which blocks all the unwanted light from the sun, and also it is developed in such a way that the factor of 15 increase you saw in the solar flux has to be balanced here itself, so that we don't have either a lot of light at the higher wavelength coming in and saturating our detector. So, the light comes through here, then there is a primary mirror and secondary mirror, which then focuses it at the detector, and the light passes through a shutter, and then the two filter wheels carrying those 11 filters, which are letting different photons with different frequency pass through and going to the detector and producing the solar images. Then there are two other payloads which are doing remote sensing. So, soft X-ray and hard X-ray, and that is essentially covering from 1 to about 30 keV with the energy resolution of 250 eV at 6 keV, and the high energy one is covering from 10 keV to 150 keV, and there is a good overlap for cross calibration, because you want to understand all the photons from 1 to 150, but you need two different instruments. Therefore, you need to understand the cross calibration, so you need the overlap. This is going to be full sun integrated, and the science goal is going to address is the explosive energy releases. How are the particles accelerated? How are they transported? What is the trigger mechanism of flares and CME processes? So, as I showed in the beginning, that you see this hard X-ray which points to the magnetic reconnection, which leads to the formation, or rather the trigger of the prominences, and that essentially is this particular, these two payloads are going to look at in the soft X-ray as well as hard X-ray. So, which one comes first, and how actually these things evolve, and eventually helps to understand the physics of these eruptions. Also, how is the cutoff energy between the thermal and non-thermal emission, how actually the energy for a given flare changes from thermal towards non-thermal. And then we have two particle instruments which are in situ, which is plasma analyzer package, which is looking at the energy from 0.01 to 3 keV, whereas the other aspects is going to look at the particles from 100 eV to about 20 keV. Again, good overlap, and the science questions they are going to look at is to see if the ejecta is just the solar wind, or the plasma is coming, they are belonging to coronal mass ejections, and that you can see because different ionizations of helium and hydrogen, helium 2 plus to helium 1 plus, and looking at the ratio. So, if you have more CMEs, there will be more less ionized helium and vice versa, and therefore, you will be able to say that now we have a coronal mass ejections which has come, but that does not still mean that is going to be geoeffective. And for that we have the magnetometer. So, the magnetometer will look at the magnetic field topology of the ejecta, and the reason that we cannot provide the magnetically cleaned spacecraft, because there are a lot of magnets inside, we cannot really say anything about the absolute magnetic field the ejecta is carrying. And these are very tiny magnetic field the ejecta would have, about nanotesla. So, for that we have two magnetometers on a boom. So, there is a boom which is hanging from the spacecraft, and the two magnetometers, or one is at the center of the boom and one at the other end, and try to understand that how much is the magnetic field generated by the spacecraft, which will be measured by the magnetometer which is closer to the spacecraft. Of course, it will have effect on the other magnetometer, but then we hope that we will be able to model the magnetic field generated by the spacecraft itself at the two magnetometers, and when the ejecta comes, then we will be able to say that the magnetic field is going to measure is because the spacecraft or because the ejecta. Once that is done, then it will be able to predict that the ICME, or the magnetic coronal mass ejection which has come into the interplanetary medium, is going to be geoeffective or not geoeffective. Okay, so in summary, Aditya mission, which is to be launched in 2020 to 2021, it will provide a multi-wavelength from hard X-ray to infrared, comprehensive view of the sun from photosphere to the corona, and it will provide in situ measurements of particles as well as magnetic field. Now, there are a lot of things which we are doing for the first time, and that is the nice thing, because you do not want to repeat something which has been done already. So, the first thing is the measurements of coronal magnetic field from space using spectropolarimetry. This is the first time any spacecraft will do it, and will do it continuously 24/7. For the first time, we are going to measure the spatially resolved solar spectral irradiance in NUV. As I mentioned earlier, it has been done earlier, but considering sun as a star. So, sun considering as a point source, but now since we can image the sun, we will be imaging the sun in these wavelengths, and we will be providing the irradiance measurement for different structures and their evolution in time. For the first time, we are having remote sensing from all the way from hard X-ray to infrared, and in situ a particular magnetic field measurements from the same platform. It has been done earlier, but different spacecraft or different instruments have been doing from different spacecraft, but now we have from the same platform. So, we are observing an ejecta, all the instruments are looking at that particular ejecta. So, you will have a full comprehensive view of any activity taking place from the sun and the evolution of the solar atmosphere in general. What we hope and feel that combining the Aditya L1 observations with those from other international missions will provide a unique opportunity to study the sun as never before, because whatever Aditya L1 is going to provide is complementary to all the other spacecraft and the missions around the world. In addition, we have our current ground based telescope MAST, which is the multi application solar telescope, and the upcoming National Large Solar Telescope, which is 2-meter class solar telescope led by IIA. We will combine that with our observations from Aditya, and that will give a full comprehensive understanding of our own star. Now, this is just the institutes involved. So, ISRO of course is providing all the funds for this Aditya L1 mission and its payloads. A number of instruments are coming from ISRO inside. So, hard X-ray and soft X-ray spectrometer, they are coming from the ISITE, which is ISAC URSC facility. IUCAA is building the solar ultraviolet imaging telescope. IIA is building the visible emission line coronagraph. PRL is building the aspects, and the other instrument PAPA is coming from VSSC, which is also a part of ISRO. And then there are a number of institutes where the people are involved in the scientific development and the science team for Aditya L1 mission. I hope that you are as excited as us building the telescope and the spacecraft, and we look forward to your participation, and Aditya L1 is going to prove its worth by providing excellent data which will help us understand our own star. So, we welcome your participation.